Hello JupyterCon, I am Madhur and I currently work as a scientific software engineering intern with QuantStack. In this presentation, I'm going to present XVega, which is a C++ backend for the Vega Lite visualization system. The motivation behind this project is that interactive computing in C++ has made some substantial progress with the introduction of the xeus-cling kernel. Further, the scientific stack has numerous projects such as Xtensor and Xframe, but there is no great support for visualization libraries yet, especially the ones that enable interactive plots. Jupyter Lab already has existing support for Vega and Vega Lite charts, and we can leverage this to bridge the gap rather than reinvent the wheel. Apart from standalone use, such a system could also be integrated in other projects such as Vega Lite. The approach is the following. Since Jupyter Lab supports Vega Lite charts with a custom MIME type, the main idea is to programmatically fill in a JSON that conforms to the Vega Lite spec and respects the notion of Grambrook graphics. It is analogous to what Altair did for Python. We'll expose different APIs responsible for filling in certain parts of the JSON. The solution is to install the library XVega. It is available on Quantaforge, and you can go ahead and install it with Mamba or Conda, although I must state that it is still under active development. The core concepts of the library are data marks and encodings. Using it is as simple as writing two statements, that is including the right header and using the correct namespace, which is xv. The central piece of the library is the chart object, which knows how to emit the JSON dictionary representing the data and visualization encodings. So marks is basically the graphic with which we should represent the data. It can be a point, line, area, bar, text, etc. Encodings are the mapping between data and visual elements of a chart, such as x-axis, y-axis, colors, etc. There are four kinds of encoding types: quantitative, which is real valued and continuous numeric quantity; nominal, which is unordered categorical data; ordinal, which is ordered categorical data; and temporal, which deals with date and time. Binning is the de facto way of producing histograms. Now, other libraries might offer special functions such as hist. Binning is a part of declarative API in XVega. Simply passing bin is equal to true takes care of the parameters and does the job. We can, of course, adjust them for more control. Aggregation helps us in getting statistics and plot them about the data. So we have functions such as mean, count, standard deviation, minimum, maximum, and many others. And we can also do binning and aggregation in two-dimensional, as we'll see in the demonstration ahead. Time series basically, again, refers to dealing with temporal, that is data dealing with date and time. And layering is sticking charts on top of each other with overlapping marks and encodings. This really helps in creating complex charts, such as a line plot that has each point boldly highlighted. The library also comes with support for transformations. Transformations are operations so that data can be filtered or transformed within the specification rather than before. Although the approach of doing it earlier with a specific library such as pandas is more straightforward, but it is useful if it cannot be done before, such as if the data source is from a URL or a JSON. And some common examples of transformations are aggregate, calculate, regression, stack, etc. We also have support for interactions and selections. There are basically three sophisticated interactions. Single selection helps you to click or interact with a single chart object, such as a point, or clicking a single bar in a bar graph. Multi-selection helps you interact with multiple of them. And interval selection helps you select a continuous region inside the chart. The basic interactions of panning and zooming can be done by binding scales to the interval selections. Now we'll go ahead with the demo. So what we have here is we import the library and use the correct namespace and define a data source. To create a zero-dimensional chart, we specify that we want to use mark point, and we create a chart object, we pass in the data, and we pass our marks. We get a zero-dimensional chart that is a single point. It's not a great visualization. To actually plot x-axis and y-axis, we need to make use of encodings. To create an x encoding, we can pass a column, say miles per gallon, and define that it contains real valued entities. So it's of type quantitative. And then we define an encodings object which contains these x encodings and pass it to the chart object. And voila, we have our one-dimensional chart. To create a two-dimensional chart, we'll have to create an encoding for the y-axis as well, wherein we plot the column horsepower, which is again of type quantitative. And the encodings object would then contain these y encodings as well, and we get a two-dimensional chart. Let's talk about third dimension. While we cannot plot explicitly three-dimensional charts, but in some sense we can define a color encoding, which basically takes data from this column origin and is of type nominal, which is unordered categorical, and these color encodings are also passed to the encodings object, and we have a beautiful visualization here in front of us. If we change the type of the color encodings to, let's say, quantitative, that is continuous, notice how the side scales here change. The representation of the colors here change since it's now real valued, so we now get a continuous smooth bar on the side. Let's talk about binning and aggregation. So binning is the de facto way of producing histograms. For that, we need to use a bar marking, and we define our x encodings and y encodings with the bin for x encodings passed to true, and we simply get our histogram. Let's say if we want more control, we can create a custom bin params object, and instead of passing a boolean true, we can pass this bin params object to the x encodings, and we get a histogram. Number of bins was 30. We can also add the third dimension again, that is the color encodings, back again to our encodings object, and we notice this beautiful visualization. Now, if we want to separate this one chart according to colors into 3 different charts, we can use a column encoding. So we define a column encoding on the same field on which color encoding was defined, and then our encoding object also contains this column encodings, and then we get a chart having 3 separate charts according to the color. We can also do binning in 2 dimensions. So we have a rectangular marking. We have binning true on both the x encodings and y encodings, and the color encoding simply tells us about the number of records each of the bins. And we can plot this chart, and here we have a beautiful visualization. Instead of using counting as aggregate, let's use mean of some column. So we can define that color encodings should take the column weight in pounds, the type should be quantitative, and the aggregate should be mean. We can also plot time series charts. Here we extract a column name known as year and define its type as temporal because it contains date or time data. And then we have our y encodings as the usual miles per gallon, and then we get a temporal chart. We can also plot the mean of the charts because we cannot really get a sense of what we're trying to show here. So we simply pass aggregate as mean on the y encodings, and we get our beautiful chart. We can also plot confidence intervals. So we have a y encoding. So CI0 represents confidence interval 0 and CI1 represents confidence interval 1. And we pass both of these y encodings and y2 encodings, and we get a chart. We can also adjust, we can also plot an area chart. We can adjust its opacity, and we can customize the title of the text here for the y-axis and get beautiful visualization. We can control the width and the height. And now we come to the layering part. Let's say on top of the chart above, we also want to plot the mean. So we define another encoding and another encoding subject. And instead of a single mark subject, we pass here 2 marks and 2 encodings. This will lead to layering, which is plotting one chart on top of the other. We also have support for transformations. So in the data that we saw before, we can actually, let's do some polynomial regression over it. We can define a transform regression. We want to regress the y variable horsepower on the x variable, which is miles per gallon, and it should be a polynomial regression. And we want to plot a line chart, so a line that fits the above data. And then in addition to marks and encodings, which we have been doing from since the beginning, we also pass the transformations here. Now these are a bit advanced examples. I won't go over them to maintain brevity, but they showcase how even tooltips and how stack transformations can create a mosaic chart. We also have a chart here which uses transformations to dynamically calculate the color of the text. So 3, 4, 6 are dark colored because they have a light background. 66, 69 are light colored because they have a darker background. There's a sneak peek on selections and interactivity. We can define an interval selection, and as we just pass this selection object here to the chart object, and we can actually interact with it. We can select a continuous region inside the chart. We can also customize it. Let's say I only want this interval selection to be able to select only the y-axis. We can also bind scales, so that will support zooming and panning. And with that, we are done with the demo. So while single and multi-selections also work, it would be futile to demo them without conditions, which haven't been implemented as of now. So that was the demo. A bit more into the library. We are actually aiming to provide a seamless experience like Altair, and so several things need to be taken care of. For a single entity, we need to support multiple types. So in the bin parameter, you could also pass a bin params object or the Boolean value true. This is done with the help of variants and visitors. And C++ doesn't support out of order keyword arguments. So we need to be able to use method chaining. And this is made easy with X property, which is a library made by Constack, which allows traitlet style properties in C++. Most of the fields are also optional. So this is made easy with XTL, which is an in-house library of Constack. And we deal with JSON through the Enderman JSON library. And we also pre-compile it to a dynamic library to increase the speed. So what are the future plans? XVega is actually in active development and not all features are available yet. We need to be able to support conditions to make selections and interactions useful. We then will add support for view compositions, which is horizontal and vertical concatenation of plots, chart configurations, and compound marks, such as box plots, etc. Contributions are welcome at the official repository, github.com/constack/xvega. And that's it. Thank you. You can reach out to me on Twitter. Thanks.